Obrigada por professor Assunção me deu uma oportunidade de dar essa apresentação aqui, mas pois que eu já esqueci muitas palavras profissionais, eu tive que dar essa apresentação em inglês. Now I will start with my presentation. The topic of my presentation is about the Crustal Anisotropy of the South America platform from receiver function analysis. Part of the work are carried out by one of my students, but I think this is some preliminary results, and later I will need some help or discussions with Professor Assunção. Then we will complete this work. This is just a first step. My presentation includes 5 parts. The first part, I will talk a little about the basic concepts and the motive of the study. As we know that seismic waves passing through minerals with lattice-preferred orientation or shape-preferred orientation will split into fast and slow waves, and this feature we call it shell wave splitting feature. To use this, to analyze this splitting feature, we can extract anisotropy of the interior of the Earth. The different origin of this anisotropy may imply different kind of deformation processes. So this is the motive of why we need to detect a seismic anisotropy. Seismic anisotropy exists in different layers of the Earth's interior, but with different intensities. And when using seismic waves passing through different parts of the interior of the Earth, we may extract anisotropy in different layers. And we can see that the anisotropy in different layers of the Earth's interior may imply different deformation processes or dynamic processes here. For the shallow part is about maybe originated by stress, cracks or faults, and the lithosphere may be frozen, may include some imprints of frozen tectonic deformation, and the asthenosphere part may include information about mantle flow at the present, and in the lower mantle may be related to some thermochemical or dynamic processes. And for the deeper part, we normally use core refracted shell waves. We normally call XKS waves. But for the shallow parts, we normally use surface wave tomography or the Moho converted waves. We normally call the PMS or receiver functions. Now, here shows some previous studies in South America. And we can see that most of the previous studies are focused on the oceanic regions around the South American plate, or focused on the active regions in the north, the Caribbean region, or in the east, the Andean orogenic belt. For the stable part of the South American platform, the studies are relatively poor, and the existing studies are mainly used the XKS analysis method to derive the mantle anisotropy. Here, this is the mainly I think the research group of Professor Assunção. But all of these previous studies, we know that parts of studies we have crustal anisotropy in the active regions, but the stable part we don't have this kind of data yet. That's why just if we know we have regional scale crustal anisotropy in this stable part. When we combine this crustal anisotropy together with the mantle anisotropy in previous studies, we may know better how the crust deforms and how the crust and the mantle interacts. So that's why we intend to process the crustal anisotropy by reserve function or by PMS shear wave splitting by using the most of the data from the RSBR stations here, shown here. Sorry. Now, let's take a look at the why we can extract anisotropy from the reserve function or PMS waves. Here shows some PMS features for anisotropic model. This is one reserve function from isotropic crust. The black line is the R component reserve function, and the red line is the T component reserve function. And this is for isotropic crust. This is one reserve function observation. All of these are synthetic data. And here we have more reserve functions aligned with different back azimuths. And for the isotropic crust, we can see that the observations of reserve functions, the delay time and the energy of the PMS on R component aligns in a straight line. And the energy on the T component is 0. Here, this part is about the synthetic reserve functions for anisotropic crust. And we can see that the R component and the T component occurs splitting here for the PMS phase. This is for one reserve function, and this is for multiple reserve functions from multiple back azimuths. And the typical feature for anisotropic crust, we can see that the delay time and the energy of the PMS varies with respect to the back azimuths periodically. And again, on the T component, the energy of the PMS is not 0 anymore. And it's also periodically here. And this one is the same as this anisotropic crust part, but we added some random noise. So for single reserve functions, we can see that the random noise strongly affect the splitting feature of the PMS. So we can't directly do splitting analysis with one single observation. And not just we can't, it's hard to retrieve anisotropy from this single trace. So, but for this here, if we use multiple reserve functions, we can see that the harmonic feature are still visible, even we have a strong noise here. So this is a feature from PMS feature for multiple reserve functions are very typical and can be used to detect the anisotropic crust, because it's quite different from this one. Because because the PMS may exhibit obvious harmonic feature, so we processed the R component and the T component reserve functions for the 466 RSBR seismic stations here. And we can see that the earthquakes distribution around the seismic station are very homogeneous. Almost all the back azimuths we have data. And here are examples for two stations. This is for the ARAG station on the north border of the Banana Basin. And this is the ITTB station on the border of the North Guapo Shield. And this dashed line, the window marked by the dashed line are the predicted PMS arrival according to previous crust thickness, we can predict the arriving of the PMS. Now take a look at the real observation for ARAG station. We can see that the oscillation of the PMS is very obvious, and the energy on the T component is also visible. But for the ITTB station, the oscillation is much weaker than this one. I mean the harmonic feature is much weaker than this station, and the energy on this T component is also much weaker than this. So just according to the image reserve function observation here, we may expect that the anisotropy beneath the ARAG station might be stronger than the ITTB station. So to utilize this harmonic feature of PMS to extract crustal anisotropy, Liu and Niu developed a joint objective function method. Here I call it JOF. The basic idea of this method tries to correct the anisotropy to be this kind of observations. So if we do a correct correction of the anisotropy, they will be looks like the corrected reserve function should be looks like this. So the joint objective are formed by three independent objective function. The first one is if the corrected reserve functions, the stack of PMS on the R component maximize, get a maximum, or if the cross correlation of each individual RF traces are maximum. This is the maximum cross correlation on R component. This is the maximum stack R component. And if if the stack of the PMS on the T component goes to minimum, goes to 0. So this is the third objective. The final JOF objective is the combination with a relative weight, the combination of these three independent objectives forms this joint objective. And this method tries to extract the anisotropy, which is normally described by fast direction or fast polarization direction, and the delay time of the slow wave. What we are trying to do is to find these two parameters for beneath each station, seismic station. To show how the JOF works, how it works, and the validation of this method, we're doing a series of synthetic tests. And here is a simple model with one layer of anisotropic crust, and its synthetic reserve function looks like this. And here is same as this, but added random noise. And here is the output of the JOF results. As this is the first slide, I'd like to give some words to describe this plot. Here shows the distribution of the objective function. All of the objective function are normalized to -1 to 1. So the blue color means the maximum, and the red color means minimum. So and the radius corresponds to the delay time. So from this plot, this is for the first objective, the second objective, and the third, and this is the joint. And these are the final results of the JOF for the case of the without noise. And here is the results for the case with contaminated by noise. And here is the input model. This is the fast direction and the delay time. And here are our outputs. And we can see that the model retrieved. The phi and the tau are very well recovered by this method. And in this case, with noise, the tau is underestimated, but the phi is still very close to the input model. I'd like to say that there are 5 degrees of difference between the input and output model. This is because our grid searching step is 5 degrees, so it's still tolerable. The difference is still tolerable. So from this test, we can see that the phi or the faster direction can be retrieved better than tau, because here tau is underestimated for the noisy case. Now, except for the simple anisotropic crust case, we do other tests, because here, based on the previous Moho map of South America, we see some variations of Moho depths here. So it's possible that beneath some stations there may be a dipping Moho. So we did another test with a deep Moho here. This model is also simple, but the crust is isotropic, but the Moho is dipping. So we can see that the PMS is also varied periodically with the BAZ, but the period of the harmonic is different from the case of the anisotropy. From now on, I will only show results with noise. So here is the results for this case. And the input model is here. The tau is 0 because it's isotropic, and we get the tau is also very small. And the phi is not real, because for the case of null tau can be retrieved by this method. But phi for the null tau makes no sense, because it can be any angle, because the polarization is forced, is not real. So now we do further tests to combine the dipping Moho with the anisotropic crust. So the PMS arrival are simultaneously affected by anisotropy and the dipping Moho. And here is the noisy receiver functions, and here is the results. And we can see that the output phi is still similar to the input, and the tau is still very strongly underestimated. So for this complicated model, we can see that phi can be still retrieved, but tau is biased, and Moho dipping may affect tau, but not phi. So when we take a look at lots of observation receiver functions, we see some special receiver functions that is different from the first 3 models. We can see that the arrival of the direct P wave is not exactly at the 0 time, and we can see that some small phases or converted phases prior to the PMS here. We see some strong phases on the T component and on the R component. Initially, we don't understand why the receiver function looks like this. But when we correspond this seismic station location with the map, we see that PCMB locates in the middle of the Banana Basin, and the receiver function looks much complicated than the cases before. So as the previous study has shown that there may be sedimentary layers here, so we test several synthetic models and finally gave a dipping sedimentary layer above the anisotropic crust without Moho dipping, because most of the Mohos in the South American, the variation is not much strong to make the Moho dipping. So the special or a feature here may be caused by a deepening anisotropy, a deepening sedimentary layer. So here is the synthetic research function that we made to make this complicated model. And we can, when we compare this here, we can see that the similarity of the faces here, they look quite similar. So it's quite possible that this kind of seismic stations may have both anisotropic crust overlain by the deepening sediment. So that's why we did a further test. Now here we made another model with a known deepening geometry of the sediments and the anisotropic crust here. And here is the output, and the phi is 35 here, input is here, and the tau is again, we can't retrieve the tau. But when we do other tests, the two model is the same, but we only change the phi. The tau is the same, we only change the phi, and we can see that the phi is well recovered, and again here phi is well recovered. So for these complicated cases, we can see that the variation of phi can be retrieved, but tau is biased. So sediment steeping can affect tau, but not phi. So in totally, so we can see that in all these complicated cases, JOF works well with phi. Now let's take a look at real station, real data. This is the two research functions for the two stations that we shown before, and here is the JOF results, and we have doing analysis of the research functions, and we have imagined that the anisotropy of this station may be stronger than the ITTB station. And actually, we can see that the delay time here, tau, is much stronger than this station. So I think according to this comparison, we see that the GOF results is still the tau of the results is still the absolute value of the tau is not interpretable, but the relative intensity of from stations to stations is still informative, I think. Now, so based on this, according to the synthetic test and according to the real data, and we see that our results is still reliable. And here shows the whole distribution of the magenta bars are the Crustal Anisotropy of our analysis, and here shows its uncertainties of phi and uncertainties of tau. And I've said before that we don't have Crustal Anisotropy for the stable part of South American platform, but we find a surface wave tomography model at 50 kilometers. This is the Adams anisotropy from surface wave tomography. And from this model, we can see that the lateral resolution is very limited. But here we show much more strong lateral variation, and we show more regional structure. And later I will give more words on the typical zoning feature here. Here is a statistics for all of these magenta bars here, the Crustal Anisotropy here. And from this figure, we can see that the phi, the faster direction, distribute in almost all azimuths, or all direction. But there are three dominant directions. One is in north-south, the other one is in north-northeast, and this one is in northeast-east. Now, when we take a further look at the crustal anisotropy together with the geographic location, we may say that for the blue shaded area here, and we say that the the fast direction, the phi is here, looks here, and this one here, this is very small, and this one. So in the blue shaded area, we can see that the fast direction is almost parallel with the TBL striking. And for the green shaded area, is here, and we can see that the fast direction here, and here, and here is almost parallel to the passive continental margin. It's around the striking of the margin. So, but this margin is also old continental rift region. And for the red area here, this is the Amazon basin, and the fast direction varies from west to east, and we see some interesting things again. In the west, this direction here, including another one on the west side of the Guapole Shield. These three, they are almost parallel to this striking of the Andean belt, but in the center one, the center of the Amazon basin here, and the other one here in the middle of the platform is almost in east-west. This direction is parallel to the mantle XKS direction, I think. Oh, sorry. Here. Okay. For the yellow shaded area here, and it's more in the Banana Basin and the Hibera Belt here, and we see a typical feature here. The fast direction turns around here. It changes in a in a small area, and the strength, the intensity of the delay time is very strong. The bar is longer than other areas. So, according to this analysis, we found the typical zoning feature of the crustal anisotropy. So, for most of the feature, we found that there is a good correlation of phi with fault striking, and most of the fault here indicated by the gray lines are from the tectonic of South America, and most of these faults or lineaments are were formed in Mesozoic in the past. So the good correlation of phi with this fault striking favors a structurally derived origin of this kind of deformation. So this may be formed during the fault formation in the past, as I think, or we may say that they are frozen. They are frozen from the past. Now, we further compared this crust anisotropy with stress field, because this stress field, the horizontal maximum stress, principal stress, the data are come from the world stress map database. They are a reflection of the current or the stress field at present. And here again is the 30 ticks for the magenta bar for the crustal anisotropy, and here is the 30 ticks for the maximum stress field, and we can see that they are different. And again, the direction of stress field is more homogeneous. They are dominant in this direction, but here it's strongly heterogeneous laterally. And again, from here in the map view, we can't see any consistency between these two kind of data. So the bad correlation of phi with the maximum stress field, this favors a stress-derived region at present. So this is nothing related to a stress field. Further, we plot the crust anisotropy together with the mantle anisotropy. The mantle anisotropy are collected from previous studies, most led by Professor Asong here, this data here. And we again did statistics for the mantle anisotropy, and the dominant direction is also very focused in almost the east-west direction. And when we take a closer look at the magenta bars with the cyan bars, and we see some interesting things. For the isolated, for example here, this direction, it's too far away to compare, but in the regional scale, they see some consistency. Here is the crust of the direction is consistent here. This too is also consistent. Besides this, here we see some very interesting feature here in this area, and we have the scale of these two data is different here. Anyway, we see that the mantle anisotropy here has also a direction rotation here, a small scale here. And the crustal anisotropy shows the similar tendency here and here in the Hibela belt. So crustal phi has a good correlation with mantle phi in the banana and the Hibela belt. This may imply there may exist a couple crust mantle deformation in this region. But I think I need more. I need a discussion further with Professor Marcelo about this part, about the interpretation of this. But this result, I think it's very interesting to me. I think that's all what I want to share with you.
Muito interessante o trabalho. Tem muita coisa para comparar depois com os resultados.
Sim, it's very muito
preliminar.
Yeah.
Mas está no caminho muito bom. Alguém tem perguntas ou comentários?
A gente tem mais dados que podem te ajudar também, né? Porque tem algumas funções do receptor lá que foi feito, né? Que eu estou até revendo, que poderia contribuir para a região norte um pouco mais.
Eu processar alguns dados no norte com aquele network ON. Mas o dado, a qualidade é muito mal. É precisar a distribuição de asymers. So if the data quality is not good, so we can't get all of the back asymers distribution. Yeah. So it's hard.
How many time do you have to do the
Oh, yeah, not 10 years. 5 years, I think. I think I put this information here, but I didn't give a word. Here. This is the data that I used here. 5 years.
A maior parte das funções do receptor vem de noroeste ou sudeste, né, que são os anos. Então você precisa ter vários anos para você pegar outros eventos em outros azimutos. Então,
I have another test, but I didn't show here. I'm not sure. Yeah, This is another test because I showed too much synthetic test, so I picked it out. Here this is the synthetic test, but with fewer back azimuths. The azimuth is from real data. It's not full. Here is the from 0 to 360. But here we picked. We take some of them away and only use the part of the data, and we finally get this result. We did this kind of test, and we can still retrieve the phi. This is for the case for most of the distribution for South American stations. For most of the stations looks like this. But those stations along the marginal, I think it's worse than.
Did you see something that for USC array by anisotropy for dense network and use not so many time but a little time? The time.
No. No.
If you see something.
Yeah, I know more about studies in China, but they normally worked in the active in Tibetan in the active tectonic active region. There are few studies worked on this kind of stable or platform, so they normally ignore the existence of crustal anisotropy. They think it's not significant.
Yeah.
But here, I think for some of the stations, especially in this Banana Basin, it's not ignorable. I think I have another slide here. Marcelo knows this work. This is from Haynes, and this I take from this paper. And Haynes observed a very strong mantle anisotropy here, very strong. So I think the strong crustal anisotropy is not ignorable, and the crust and the mantle have occurred coupled deformation. So if they are coupled, so the delay time can be some. Yeah, they are strengthened with each other. So that's why maybe I didn't discuss this here because it's not mature. I want to later talk with you. Yeah.
The mantle, the strong mantle anisotropy is usually interpreted due to shear strength.
Mm-hmm.
Whereas the crustal anisotropy is usually interpreted as a result of compression.
Mm-hmm.
So
yeah,
it is not easy to see how mantle deformation will be coupled with crustal.
Yeah.
But it is interesting that the directions are the same.
Mm-hmm.
Another thing that you see, the depth of the sediment is a good result for us. If you use the model that you use to create the synthetic, and for us, it's if you have a good resolution about the deep and the
the geometry of the deeping is also resolvable, but it's also very hard. There are trade-offs.
The dipping mode must have an effect also.
Yeah, have. For this method, it's I'm trying to find the 4 parameters, including the dipping geometry and the anisotropy. The efficiency is very hard, but theoretically it's realizable.
May I have a question? Did you try to run any test that you put 2 layers inside with the crust? For example, one with a different anisotropy direction.
Yeah.
For example, the upper
I didn't show here, but this test is also applicable to mantle, because if you have two layer with the anisotropy is different, they are the polarization becomes too much complicated, and the delay time is, or better, you can't detect the anisotropy. Yeah, it's very hard. So that's why normally for the mantle anisotropy we still have no depth resolution. For the crustal also we can't have. That's why we have to study layer by layer.
How much dependence do you have on the window you choose to
Yeah, good question. Yeah. We also did this kind of test, but I didn't give here. I didn't remember how I gave, but I can. Normally, for this station, I will pick the H-kappa results from your study and use the VP from your model, so we can predict the delay time. And we can imagine I think this is the period depends on the Gaussian filter that you use. So the window will covers the. I think. Wait, where is the synthetic data? I think no. The green one, I forgot where. Here. The width depends on this, the width of this harmonic, and this depends on the width of the PMS, and the PMS depends on the Gaussian filter width. Do you understand? So, this windows varies with Gaussian filter. I defined it variable. If you use the alpha Glange alpha, so this will be neither or vice versa. Yeah. But it's very important, because if you choose a wrong window, it fails. It's not correct. So the best way is that we use the better solution to correct all of the reserve functions and show them again. This is the best way, but I didn't realize yet.
One other point is that in the sedimentary basins, you should also expect anisotropy because of the layering. But this will be radial anisotropy, and then it will not.
No. I didn't consider anisotropy in the sediments, just only in the crust, crystal crust.
But even if there is anisotropy in the sediments, it should not interfere with this analysis.
I think it will influence on the tau intensity.
Okay.
The test means that this is because the sediment layer will influence the PMS arrival. They pushed them in a different. Yeah.
There is a question from YouTube. Anderson Farias do Nascimento asks if you have compared your results with shear wave splitting results from earthquake local data when available.
Sorry?
He's asking, you compared your anisotropy results only with SKS, but in the Northeast, there are results of shear wave splitting from local earthquakes. So these are measured directly at the crust. So he's asking if you.
No. I don't have this kind of data. I think it's necessary to do this kind of comparison, yes. I mostly do this analysis based on open data. For some data,
But there are a few papers on upper crust anisotropy from local earthquakes. So
Yeah.
I can give you,
Okay,
especially in the Northeast.
okay,
So
okay,
I can
yeah,
give you-
yeah,
we can compare.
okay, thanks.
I have a question. Very interesting work. From your synthetic tests, it seems like you can't recover tau very well for all the cases. Is that correct?
But we see that they can retrieve the now tau.
Direction, right?
Yeah. The isotopic case they can retrieve. They know that's why we show also this the point without anisotropy.
Yeah. Because my question is, do you compare, for instance, a station close to Pantanal Basin and another one in the Amazon crater? And then you'd say that one is weak, another one, for instance, is strong. So my question is, how much of this uncertainty from your method?
You are right.
influences that
I
analysis?
will show you this figure. I didn't talk. I even have no time to talk with this figure here. Yes, here. Now, when we look at the results, we'd better look at here. Normally, we need to take a look at the. I didn't, but here I put a description about the uncertainty. I will give a little bit word here. For example, these blue circles. This means that we have a large delta phi uncertainty in direction. And the size of the circle is scaled with the uncertainty of tau. So the big circle means that we have large uncertainty in delay time. And the blue circles means that we have, but blue small circles we can ignore because small circle means, no, sorry. These short bars means the intensity is very weak. When intensity is very weak, the uncertainty of phi make no sense because it's possible isotopic. Yeah. It doesn't polarize. So these blue circles we can still use because it's still interpretable. But for some big, for example, this kind, anyway, this I didn't say, but I kept all of the acceptable results. Oh, I processed 66, but I only kept 50. What's the criteria to take them out? Normally, we judge if the direction, the fast direction is similar or not according to a half quadrant. That means 22.5 degree. So if the delta phi is larger than this value, I think the results is not acceptable. So all of this data here, although it's blue, but the delta phi is smaller than 22.5 degree, or it's smaller than a half quadrant. This is, and for the tau, as we know the test, the uncertainty is very large. And the global total uncertainty in tau is about 0.3 second for the global average. So I take 30% of this value as the acceptable uncertainty. So all of the uncertainty in tau smaller than 0.15. I think it's acceptable. All of the uncertainty greater than that, I removed them. So that's why here these I show the map, but I didn't. So, for example, I think you mentioned here.
I believe it was the one to the right of what I showed.
This one?
Was mentioned the IT.
Which one?
ITTV.
Yeah, this thing.
Wait. Here.
Yeah.
This, it's very weak.
Yes.
And the uncertainty in phi is blue. that's what I see the case. Here, there may be no or very weak anisotropy. That's why the polarization direction is very strong. Because you have no polarization here. It can be any direction. So the uncertainty is very large here. So I keep this, this is, you can see that, for example, this here, it's very weak, but the uncertainty is even larger than the tau here. But it's very weak. We can't see the results. Yeah. So that's why when I described the results, I normally look at the stronger. And this one is acceptable because the circle is very small and the color is warm. So these results are very reliable comparatively. That's why what I told you is results reliable, and the rest, I think we need more observations. Yeah.
Thank you.
You are welcome.
For the parallel basing case, I think the parallel basing, it's one place that there are some issues about underplating ideas.
Yeah, that's.
So maybe this is something that you are observing there, that the similar striking as the mantle because it's underplates. And this would explain the very high thickness that we observe, that we are not really measuring crustal material, but underplated material depths, plus the indication of anisotropy from your methods, just showing that the receiver functions are not really converting on the crustal material, but on the underplating below the crust.
Yeah, I can't discriminate this.
You can, and well, actually, the way I see your results, your result is really favoring the underplating idea more strongly, and that the very thick crust that we attribute to the parallel basing, it will be discussable if it's really crustal thickness or underplating thickness.
Okay, thank you.
Yeah, no.
I think
I'm really bad on interpretation.
Yeah.
That's the way I see your results. But it's a good contribution to understand what's really happening there.
Yeah, I think in Chinese, I don't know how to say in Chinese, we have a phrase, it's not a valuable study, but it's useful.
It's very useful.
Tem mais perguntas ou comentários? Eu tinha preparado uma apresentação das pesquisas que a gente está fazendo aqui no grupo de simologia, então isso não precisa ir para o YouTube, então quem quiser ficar aqui para a gente ver, e eu vou apresentar então também um resumo de algumas das pesquisas que a gente faz, e vai ter bastante coisa de anisotropia também para a gente comparar depois. E tem um cafezinho aí, vamos dar uns 5 minutinhos de intervalo para o café, quem quiser. Coffee break?
Oh.
Very nice to meet you. My name is Carlos.
Okay. I read your paper, right?
All right.
Sorry, I can't correspond to the pronunciation.